Okay, so that brings us to the compressibility factor. What the compressibility factor can do is it basically serves as a correction factor for the ideal gas law. So what does that mean? Well, that means I can have P little v is equal to Z R T. And this is and often they'll use the adjective here, the generalized compressibility factor. Generalized compressibility factor, and that is the Z value, capital Z here. So pressure times volume is equal to a Z value times RT. If Z is 1, if we just say Z is 1, that means the substance is ideal. PV is equal to RT, 1 times RT. Not, again, no gas is completely ideal. All ideal gas law is always an estimate for any substance. And so what this does is it allows us to put in kind of a correction factor, a value that is not 1, a realistic value that matches more of a realistic scenario. What the Z value is the Z values we've taken, scientists and researchers have taken actual specific volume values. So let's say they put a substance in a cylinder, they expose it to a certain amount of pressure and a certain amount of temperature, and they actually measured the specific volume of that substance, the actual specific volume. And if we compare that to the value that we would get if we estimated it using the ideal gas law. So it's similar to an efficiency almost, where you get this ratio of things that are the same. You're comparing two things that are the same. The Z value is a comparison between the two. How close is the actual value, if I have actual substance in front of me, compared to what I would compute using the ideal gas law? That ratio is the Z value. Now, that's not something we would be able to find or determine short of having a bunch of experiments. Well, we're sitting in a classroom with a textbook and a calculator. We can't do experiments like this, but people have over the years, and we can rely upon those. That's what, as engineers, that's really our goal is to utilize existing scientific and mathematical knowledge to solve problems. So this knowledge exists. This is out there. People have researched this. So that you'll find this diagram in your book. I went and looked it up here. In the 10th edition of the text, this is page 128. Page 128, you see there. Now, the markings on this diagram, just to call your attention to those, the markings on this diagram, they've given you a legend down here. The X's are methane, the circle is ethylene, the darkened squares are ethane, for example. And there's also water and some other substances in here, okay, propane, carbon dioxide, etc. So once you kind of see that, hey, it's a bunch of curves, then you can just basically ignore the dots, the markings. All they're trying to communicate to you is, hey, these curves match. Notice how closely, if I put real data on this graph, notice how very obvious curves begin to appear. There's some outliers, but you can see there's a pattern. My goodness, look down here at the bottom of this. Look how closely this pattern matches. And look how well this pattern up here matches, right? So what they're saying is, hey, every substance behaves very similar to these curves. And so given a reduced pressure, and you can go, let's say I've got a reduced pressure of 2, and I come up here and I've got a reduced temperature of 1.2. And so, just for example, we'll do an example where we put some numbers to this. So let's say I've got a reduced pressure of 2 and a reduced temperature of 1.2, and I come over here and that tells me my Z value is like 0.58. Right? And so I could go into this equation, I could plug in 0.58 at that known situation, calculate the V value, and that's going to be much better than what I would get with the ideal gas law at that point for any substance. Okay. Now, notice I didn't say temperature or pressure. I said reduced pressure and reduced temperature. What does that mean? Well, that means to be able to put all these substances on the same graph because they all behave differently at different pressures and temperatures. But what we found is that there's a reduced quantity that they all behave similar with respect to. How we find that reduced pressure is I take the actual pressure for the substance in front of me divided by the critical pressure. And I can do the same thing for reduced temperature, where I take the actual temperature, again, absolute for both pressure and temperature, no gauge pressure, no Celsius or Fahrenheit, no relative scales of temperature. If I take the actual temperature divided by the critical temperature, then I get the reduced temperature and the reduced pressure. Now, the next question is, Steve, what is the critical pressure and temperature? What do those mean? Remember on this diagram that we drew last few times, I can put P or T on this axis, and I put volume down here. Whether it's P or T on the axis, I get this dome region. And remember, we said at the very top of this dome, that has a special name. Pause it and go remind yourself what that special name of that point right there is. What is that point named? You got it? Okay. You understand now where that CR value comes from. That's the critical point. It's the top of the dome. The point where the substance stops behaving like, stops going through a visible transition from liquid to vapor. It just magically goes from one to the other. And that's when that's the critical point. And so what we found is that that critical point is different for all of these different substances. But if I compare the actual temperature with respect to the critical point temperature and the actual pressure with respect to the critical point pressure, and compare all these different substances, then these patterns emerge, these curves emerge. Right? And so that's what we then use to determine what our Z value is to go into the ideal gas law, and this can account for some of the error associated with the ideal gas law. It basically serves as what we call a correction factor. It improves the ideal gas law. This is one of the easiest ways to really improve the ideal gas law without a whole lot of effort. Now, from there, that figure there that is in the 10th edition, this is in the 10th edition, this is figure 348. Now it's something different we're in the 10th edition of Chingle and Bowles. If you're in another edition, it's probably some other figure number, but in our edition, that's figure 348 on page 128. Okay. So figure 348, that works really well if you're given pressure and temperature. But if you're not given pressure and temperature, there's a figure back in the appendices that you'll want to use. So if we go look at that, let's let this load. So this is available. I figured this might be better than me trying to show you the document camera. This is available to my students in Canvas. This is the appendices. I've got this out of a 6th edition. In the 10th edition, they made an improvement that where you see these two are on one page in a textbook and all the way up to the 9th edition. In the 10th edition, they split these out. They put this one on top. They put this one in on one page by itself, and they put this one on one page by itself. Okay. But notice that these are a lot harder to read, right? You'll want to zoom in on these, right? And so what I do if I'm trying to use the one in a printed textbook, I'll take a picture of it on my phone and then zoom in. Now, again, with the new one, the newest edition of the textbook, it actually takes up a whole page. They give you like a whole page. It's a lot easier to read. I don't know how quickly I can flip to it in here. But this table, where is it? This figure is between the R134 tables and the tables immediately after that. So it's basically immediately after the R134 tables, right? So I don't know how well you can see that here, right? That is that first one that's on a whole page, and that second one's on its own page. So in the 10th edition, they did that. That is figure A15. Figure A15 in just about any edition of the textbook. Okay. Now, this works just fine, or actually well, if I'm given pressure and volume or temperature and volume, because there's these reduced volume values down here. These reduced lines of volume, which are these dotted lines. Another thing to mention is notice the scale of the reduced pressure down here. Excuse me, this goes from 0 to 1. This goes from 0 to 1. Whereas if you look at the next one, this goes from 0 all the way up to 7. So basically what that's telling us is from 0 to 1 up here, this area up here, this is a zoomed in version of this little block right here, right? So if I know I've got a very low reduced pressure, this chart will actually give you a much better read, much better estimate than this one will. This one works good if I've got a much higher pressure, okay? And so again, you can see when Z is 1, that means your substance is an ideal gas or behaving ideally. If your substance is not 1, you can use this to improve your estimate with ideal gas law. Okay. Now, again, if I'm given pressure and volume or temperature and volume, I've got these lines of reduced volume on here. And so we can use that then to find, so we use figure A15 if I'm given pressure and volume or temperature and volume. And that's because then I can use the lines of reduced specific volume where that's equal to the volume that you're given divided by R times the ratio of temperature critical to pressure critical. And then I can plot on a line of reduced volume and line of reduced pressure or line of reduced temperature, find where they intersect, go over and find the Z value that corresponds to those, and then solve, go from there. Okay. So ideal gas law serves as a reasonable estimate for behavior of gases. Here's the bottom line. If you're working with air, in my class, if you're working with air, if you're working with nitrogen, if you're working with oxygen, if you're working with carbon dioxide, things we normally see in the gaseous state out here in the real world, you are more than welcome to treat them as an ideal gas. If you want to go through the trouble of finding a Z value, and improving ideal gas law, you can. I'm only going to ask you to do that one time on a homework problem, just so you've gone through it and you've at least seen it, and then we're fine. If you need something better than the generalized, if you need something better than ideal gas law, the generalized compressibility chart, the Z value, is a very effective, powerful, quick tool to use. That's better than the ideal gas law. If you need something even better than that, or something that you can program into a computer, in your text, if you go to section 3.8, it gives you information to utilize something like van der Waals, Benedict Webb Rubin, Beatty Bridgman. These are really powerful models that you can use that are much more advanced and much more robust than the ideal gas law. And you can see this is on a logarithmic scale, but it's the same chart that we saw earlier, right? This guy back here, this guy. So where this is not quite a logarithmic scale, it is to an extent. They're basically showing you the same information here on this chart. Again, this is also from the Changle and Bowles text, but they're showing you then using some of these, let me move me out of the way. They're using some of these other more advanced models. They're showing you the error associated with these different equations at given pressure temperature combinations. So remember up here at the basically at the critical point where the ideal gas law was like over 100% error at these high pressures. Not the case with some of these other models, right? And so your tables a lot of times in your book are made using one of these models, and some of the really advanced systems, when they go to generate those tables, they'll go through and they'll look and say, okay, well, in this pressure temperature combination, we're going to use van der Waals. In another pressure temperature combination, like, over, I don't know, over here somewhere where there's somewhere where Benedict Webb Rubin probably is the best. Yeah, right here. See how Benedict Webb Rubin is the best at this pressure temperature combination. And then somewhere over here, using, I'm sorry, that's Beatty Bridgman is the best one here. but Benedict Rubin would be the best one here. So given a certain pressure temperature combination, they'll determine which is the best model, and they'll use that to make the tables with. All that to say, I'm not going to test you on these other models. It's just a, hey, if you need something with more teeth in it or something that's easier to program into a computer, go to your old thermotext, go to the end of chapter 3, and there's some better models in there. Okay? That's a beautiful place to stop. That brings us to an example problem, and we'll go from there. Okay?